single-valued celestial amplitudes.
So thank you. I would like to thank the organizing committee for inviting me to this beautiful place. The only thing is I have from there is the nice postcard that you can see, and of course, have to stick to virtual reality. Anyway, my talk is based on 2 parts of recent paper written with these collaborators. I'm highlighting here the name of Ben Zhu, who is my student graduating next year, who's a really key player in all these developments. So the title is Single Valued Celestial Amplitudes. Here's the flow chart of my talk. It is a loop. So I will start with from celestial amplitudes, as we know them, which are Mellin transform of standard amplitudes, for reasons that I will explain in more detail in a minute. I will take a shadow transform on one of gluons that will lead to a 4-point correlator with one gluon represented by the shadow operator. I will point out some problems with this shadow correlator. The real problem is that it's actually not well defined because it has a branch points. It's not single valued. But in the next step, what I will do, I will follow approach, which is very a simple approach, which is adopted in minimal models. I will construct in one step a single valued version of the shadow correlator. Now here the miracle number 1 will occur, while the original correlator was had no good crossing properties and had no there was no way to make a connection with the operator product expansions of gluon operators that we know. This new single valued shadow correlator will be consistent with crossing symmetries and will be defined on the entire complex plane and will agree with all known operator product expansion coefficients that we know in celestial conformal field theory. So that will be the first miracle. Now, what I will then do, I will again, following the same strategy as minimal models, I will construct integral representation of this single valued shadow correlator. This will be by following the approach of Dotsenko-Faddeev. That will lead to integral representation. And here miracle number 2 will occur because this integral representation, this integral, can be written as shadow integral of some other function. And this will be actually, this function will be a new celestial amplitude, which I call single valued celestial amplitude, which will have all good properties that you need in conformal field theory. It will have all good conformal and all good crossing and bootstrap symmetries, and again will agree with all known operator product expansions. Okay, so that's essentially the outline of the talk, and at the end I will actually discuss in more detail the properties of this single valued celestial amplitude. All the way throughout this talk, I will be using standard tools, which is like crossing symmetry, crossing equations, and Miguel explained, operator product expansion and conformal product expansion, and it will be very useful to lead us from the beginning to the end of this loop. So I should also mention there is another parallel work of conformal blocks, and I think Anna will be talking more. I think next talk, Anna will be talking about this work. Okay. Okay, so the first step, here's the first step. Starting from celestial Mellin amplitude, we'll perform shadow transformation that will lead to this shadow correlator. Why we do that? Okay, the point is that while the positions of the operators of primary operators representing gluons on celestial sphere are relating to their momenta, and their positions actually are constrained by momentum conservation, and the conformal invariant way of characterizing this constraint, which actually comes from the planarity of the 4 particle scattering, is that the cross ratio of the 4 positions must be real. And actually, if you look at one channel, for example, what we call S channel, and for dimensions, when gluons 1 and 2 go into gluons 3 and 4 in final states, then actually this cross ratio is also has to take a value which is bigger than 1. And that's actually, I would like to make very clear from the very beginning that I will just sticking to one 4-dimensional channel. Okay, so it will be always scattering amplitude for 1 and 2 goes to 3 and 4. Now, if you look at this correlator, well, already it's not a typical correlator because the insertion points are constrained, but also it happens that for 4-point functions, you have this constraint is implemented by a delta function. So actually this correlator is distribution valued. Okay, so it is not again not a typical thing for a 4-point correlator. So actually the reason for taking shadow transform is to extend this correlator to the entire complex plane of the cross ratio. Now the cross ratio involving the position of the shadowed gluon. Okay, and then so you do this well-known transformation, and okay, and that's what I'll be talking about. Actually, this shadow transform exactly is motivated by earlier work of actually there's a very early work like 4 years ago by Sabrina about the subject, which is very interesting. So there may be some relation between shadows and shadowing and considering incoming and ongoing operators and so on and so on. Okay, so that was essentially the motivation. Okay, but now you may ask the following question. You may ask whether this correlator, which constructed by shadow, whether it's a really good CFT correlator. Now we know that it's defined on the entire complex plane of the cross ratio. Now, when you look at it, I'm writing, okay, first of all, I should mention that we're writing any correlator as a function of cross ratio. That I mean by that something which is in text we call a partial wave, which means I fix position points. I think 1 in this case, I always said 1 to infinity, 2 to 1, 3 to x, and 4 to 0. So there's something which is called G1 to 4 3. There's a notation which in the paper we use the proper notation of differential stuff. So anyway, so then when you compute the shadow correlator, in general, okay, after you perform this integral, this shadow integration, it's a complicated function. It's one of Appel's functions. However, there's very significant, and it's sort of hard to discuss, okay, for the moment. There is a limit in which this shadow correlator becomes very simple, and it is the limit in which you consider the case when the shadow is soft, which means when the shadow has dimension 1. And then the amplitude consists, of course, the full amplitude consists of 2 partial amplitudes with with appropriate color factors. And then all these, when you look at one partial amplitude, it's just because it's a holomorphic part times anti-holomorphic part, each of them given by some hypergeometric function. So we are now in, so when you have hypergeometric functions, we know very well what are the properties when you handle this problem. One interesting thing that if you perform conformal block decomposition of this one, for example, this one partial amplitude, then you find that actually something interesting that the anti-holomorphic part corresponds only to one conformal block. That's something which is this is something which is common, which is familiar from minimal models, and which actually will be very useful in this following construction. Well, another thing, there's something, however, which is not so good about the shadow correlator. If you take limit x goes to 0, which in this case, the cross ratio going to 0, then you see which corresponds to essentially taking a limit of coinciding points 3 and 4. Then you find this behavior, and this is actually not what one would like to have, because actually when you take a limit 3 goes to 4, okay, that limit should be governed by the operator expansion of gluon number 3 and gluon number 4, and actually, so which is written here, and which should go simply like a simple 1 over x. So with the known beta function coefficients. So this operator product expansion is doesn't look good at this point. Well, another thing which doesn't look good but looks really very bad is that if you look at the conformal block decomposition and the channel and something which is called two-dimensional U channel, yes, 2 and 3, first you just bring together. You consider operator product expansions, okay, and first when 2 goes to 3, you find that actually you find here that there are conformal blocks with complex spin. Now, well, conformal complex spin is bad, is really bad. The reason is that if you go to if you go to the limit of x goes to 1, you find, and it's not surprising because that must happen with a hypergeometric function, but there's a branch point at x equal 1. And this branch point at x equal 1 is directly related to the presence of complex spin. This is not good. So this means that this correlator is not, again, is not a good correlator. Okay, it's not a defined, it's not a well-defined single value function on the complex plane. So we need a clearly you need a single, it construct a single value correlator, and then the hint comes from minimal models in which you have conformal, you have Verma models which are degenerating at level 2, and this is again you can look it up. For example, in Francesco, these are very simple models in which you have each of in which you have exactly the case in which the conformal, you have essentially, if you look at one channel, you have just 1 or 2 conformal blocks. And actually what you do in this case, okay, in these minimal models, they are usually spinless, yes, so you think about them without spin, you do not consider spin. Then you add the extra, what you do, you make this correlate a single value, but by adding another term to the 4-point function, which represents the contribution of a shadow block. In our case, we have, it's sort of a little bit more subtle because we have anti-holomorphic part, looks like from minimal model. The holomorphic part looks like, contains actually infinite number of holomorphic conformal blocks. So it's type of a heterotic model, but actually it happens. One finds that one can make it single value, but just adding one function, which contains this anti-holomorphic block associated with the shadow of the original block. Okay, so just add one term, and you get a single valued correlator. Now, this way you obtain the single valued shadow correlator, as I mentioned before, by following this approach very similar to minimal models. Now, as one finds, and I will explain it in detail in a minute. Well, first of all, it's sort of obvious there's no complex spin, yes, because I made it single valued. Then it has correct OPEs, which agree with all OPEs that we know, and it has all crossing symmetry properties, and bootstrap, you call them sometimes, okay? So it's a good CFT correlators. And you will see actually details later when I will be able to remove the shadow, but just to tell you in a minute, tell you now in advance, when you take limit when the cross ratio goes to 0, which corresponds to insertion points of 3 and 4 coinciding, then you find that it really goes like 1 over x. So actually it reflects, it agrees with the well-known operator of product expansion of the gluon operator with the correct operator product expansion coefficient. So here we are at the single valued shadow correlator. Okay, so now the next step is that, in single, again, minimal models, the correlators have also integral representation, which is related to the fact that you construct them by inserting so-called screening, charge screening operators. Actually, so although this correlation functions, which contains 2 terms, each of them being some hypergeometric function, which is a real line integral, you can apply the Dotsenko and Fatiev approach, which these days you would call, people call it KLT, okay? And from this, from those products, you can construct, you find that actually the sum of 2, which is the full correlator, can be written as a complex integral. These complex integrals for each partial amplitudes are written there. And you see that they are very simple. Actually, they have a Koba-Nielsen form of very similar to well-sheet integrals, in which these conformal dimensions are related to kinematic invariants. And actually, they look really like string well-sheet integrals. One can follow this path and actually also find another integral representation of this single valued correlator, which will be rated more to open string. And this is, you can find something which is called single, express them, you can write them down as the so-called single value projection integrals of Brown and Adler. It's something that we studied with Stefan for a long time. But it will be not, I will not be using it here anymore. All right, so now, so we have this shadow integral representation. And so it is a complex integral. The question, where we started from the shadow, so can we write it as a shadow? The answer here, surprisingly, is yes. So this shadow correlator can be written as a shadow of a 4-point function. And this 4-point function is written here. Before I talk about it in more detail, I would like to make one important remark, that as you see here, I started distinguishing between incoming and outgoing the operators associated to incoming and outgoing gluons. I'm using this notation with plus epsilon corresponds to outgoing particles minus epsilon is the notation originally used in the paper by Raclariu, Strominger, and Yuan. So this will be important. When talking OP, actually, I will have to be very careful because I have to distinguish between OP, let's say, of 2 incoming operators, of 1 outgoing and outgoing operator. But anyway, the result, the single value amplitude that you obtain in this way is has a very simple form. It contains something which in amplitude literature goes under the name of PT denominators. Okay, and these are exactly the same structure. Then you have the MHV amplitude and a nice super amplitude. Okay, so this part, there are 2 parts for 2 partial amplitudes. Then there is a conformal factor, which essentially is here just to ensure correct conformal weights for external particles. So it essentially PT denominators dressed with these conformal factors. And what is very, again, something which is very important, that there is an overall normalization factor. And this normalization factor is completely fixed when it's completely fixed by the requirement of this single valuedness. So while the original celestial amplitude had one, this overall coefficient, overall weight, overall factor in front of the single value amplitude is completely fixed by this construction. So now what I will do next, I will just show you how this OP, crossing symmetry, and bootstrap are satisfied, work well with this single valued amplitude. So I talk about for a minute about the leading operator, product expansion, crossing equation, and bootstrap. And then I will tell you something about beyond leading operator, product expansion, and about the conformal box spectrum. So the leading, so let's start from the leading operator product expansion. Now the overall coefficient of this amplitude, which I'm telling you fixed uniquely by this whole construction, by this construction, is something which I can be written as a product of beta functions. Okay, and now so what I will do, this is these are conformal blocks, and the channel drawn here is two-dimensional channel. Okay, so then you look here, the first, so you just want to follow factorization chain. So first we go 3 going to 4, and for that this gives you this beta function coefficient from the well-known operator product expansion. Okay, so that's the first, this red factor. The next thing is so now we are at the 3-point function. At the 3-point function, next step is we take 2 goes to 4, and then the operator product expansion, okay, is actually involves 1 incoming, 1 outgoing particle. So it is different from, it has a different form, and it has actually 4 terms. And well, one of those, one can show that actually the one term, the operator, the only operator on the right-hand side that contributes to this 4-point function is the one with this coefficient here, and green, and actually the coefficient that the second factor which you get here, and then so this works, and then finally you need another factor, and it comes simply from the 2-point function and from the 2-point function of the remaining 2 primary fields. Okay, so it has the amplitude has correct factorization properties. Okay, it is consistent with the OP. What about you can ask the following thing? Okay, so whether this is consistent with crossing symmetry, bootstrap, and crossing equations. Okay, so in other words, I told you already that I get this that I get the leading OP term from this 2-dimensional channel, yes. But again, crossing equation are telling you that the OP applied in this channel should be equivalent to the OP applied in a different channel. This is here, for example, we have U channel, and then one has to be careful because here we have 2 incoming operators, here 1 coming and outgoing, but you can check indeed that you can follow another factorization chain, which starts in 2 going to 3, and then, okay, as before, and you will end up with the same result, with the same coefficient. So this amplitude, the single value amplitude, has correct crossing symmetry and bootstrap properties, and is in agreement with all known OPs as you saw them. You may ask also, may I ask a question, how much time I have?
Yes, so I was just about to say you have 5 minutes.
5 minutes, okay, that's perfect. So you may ask also the question, what happens beyond the leading order of operator product expansion? And then what you find, so you know that external particles are gluons, so that, well, let's talk about SU2, because that's very simple to discuss. And then you have 2 triplets of SU2, so they can produce a singlet, triplet, or a quintuplet. And actually, then from 2 gluons, you can produce a primary field with higher dimension, with higher conformal dimension. And actually, these operator product expansion will involve Klebsch, obviously will involve Klebsch-Gordon coefficients. And again, you can check this crossing equation. You can extract these operator product expansion coefficient, and you can show actually that this crossing symmetry also holds at higher beyond the leading over of operator product expansion. So this is okay. So everything here is consistent. In general, actually, what you find for a general group, gauge group, you find that the primary, the conformal blocks, which are propagating in any channel, are in any all representation which contain in the product of two representation and the product of two adjoint representations. And you find conformal blocks which have in all channels. You find the same conformal blocks. They have you find now you find gluons, so you find the original, the principal series with dimensions 1 plus I lambda. But we found generally we find all primaries with higher dimensions labeled by integers. But we always have integer spin. It must be the case because this amplitude is single value. All right, so to summarize, okay, here I rewrote this single valued amplitude just as a partial wave, yes, and the 1, 2, 3, 4 channel, and it is given by a very simple expression. Okay, this reflects this PT denominator, and here these are two partial amplitudes. So this single valued amplitude is single valued. It agrees with known operator product expansion, has all correct crossing symmetry and bootstrap symmetry, bootstrap properties. And as I mentioned before, it's related to MHV amplitude, is related to Nair super amplitude. So actually, this similarity with Nair super amplitude suggests that it's related to this amplitude is you should be able to obtain somehow this amplitude from twistor space, because Nair's super amplitude is naturally realized within a twistor strings. Now, what about the original Mellin amplitude? Well, you may think that there may be a way of improving it and somehow constructing the single valued amplitude by some time of improvement of Mellin amplitude. I'm rather skeptical about it. So I think that it's more likely that this single. I think that at the end, the celestial conformal field theory should use the single values amplitudes as a starting point for developing full, like two-dimensional, holographic conformal field theory. So that's why this explains this crocodile here. I think it's difficult to get from the Mellin amplitude to the single value amplitude, and yeah. All right, good. So this is essentially everything, and so thank you very much.
Thank you very much for the interesting talk. People want to thank Tomasz. Are there any questions about the talk? So actually, there is. Okay, so actually, let me. Atul, if you want to unmute yourself and ask your question.
Yeah, thanks. If you had, so now that you have the single valued amplitude, could you try to spot a prescription for extracting the amplitude from it? Suppose you had a CCFT that gave rise to the single valued amplitude, the single valued correlation functions. Could you spot a prescription to sort of extract just the 4-particle scattering amplitude from it? Like the not single valued part, the half S1, I1.
Well, you see, yeah, I don't think that you can get there from Mellin. Okay, so this is not to extract, as you say. The question which you are sort of asking in some way, whether this single valued amplitude is really an amplitude which you can get from, for example, in twistor space or something. Okay, for example, the one obvious question you would ask whether it really can represent some scattering amplitude. Yes. So now I can tell you, I think that is indeed the case, and the reason is that you see that. You know that the MHV amplitude, here I use the holomorphic representation for the amplitude, yes? Okay, so, which is in terms of these wedge products, yes? But by using momentum conservation, you can use also something which is called anti-MHV amplitude, which will lead to the single value amplitude, which will be actually complex conjugate, what you have written here on the top of the slide. The two will overlap when Z is equal to Z star, where Z is equal to Z bar, which means that the momentum is conserved. So I think I really believe that this amplitude can be constructed simply as some type of a scattering amplitude in twistor space. Does that answer your question? Or so in other words, for me, the question is not, now I know every time how a CFT of that, well, and this limit lambda 1 goes to 0. For me, the problem is how to produce this, single value amplitude as a scattering amplitude and related to 4-dimensional Young-Mills.
Yeah, because if I remember correctly, Slotnikov and other people showed that momentum conservation requires that delta of Z minus Z bar.
No, so that means that Z equals Z bar, of course. Z equals Z bar is the momentum conservation. So you see this, you have to think about this ASV on the top as extension of some scattering amplitude away from the momentum conserving configuration. But I'm telling you that when Z is equal when the momentum conserve the momentum on a configuration with respect to momentum conservation, Z equals to Z bar, and I see that and I see it as I explained by connecting to MHV bar amplitude.
I see.
Yeah, so I think that at the Z equal on the real line, it should be related to some regular scattering amplitude.
So when you restrict to the real line, you should be able to find your usual scattering amplitude somehow.
Yeah.
Okay.
Yeah.
Miguel, if you want to.
So thanks for the talk, Thomas. I have some basic questions, basic confusions about all this.
Okay.
So you're talking about the conformal block expansion, but I mean, here you are doing perturbation theory, right? So, for instance, you would expect that the general order that you would get things like derivatives of conformal blocks with respect to scaling dimensions. This could occur. So,
well, this is amplitude, which is tree-level amplitude in Young-Mills. That's all what it is. It's one amplitude. And it has,
but from the CFT perspective,
it is conformal block expansion. Again, the conformal expansion we are using is the global conformal blocks.
Sure, I understand that. But my question is, I mean, so this is supposed to be the leading term in the CFT expansion?
Yeah, I thought that's.
So, for instance, when you do ADS CFT, you start off with the disconnected diagram. These give you the leading OP coefficients, and then when you look at the interactions, if you decompose the interactions into conformal blocks, you get things like derivatives of conformal blocks because they are correcting the leading order result. So here I imagine, for instance, that if you would go to loop level somehow, you should get derivatives with respect to scaling dimensions of the thing that you found here, for instance.
Yeah, it would be interesting, as you're saying, it would be related to higher orders, to the loop corrections and Young-Mills, yes. So that would be really something. We could relate somehow two-dimensional corrections to four-dimensional physics. Yes.
Yes, I guess. Or turn it around. I mean, in this OP, do you see the identity?
What do you say?
In the OP, do you see the
OP?
identity?
Your OP is an infinite. There's infinite number of, there's continuous, an infinite number of primary fields here.
Yes. And is there the identity in this set of group or not?
And do you have a operator, two gluons have infinite terms in operator product expansion. Yeah.
So there's no identity.
Yeah, that's I'm not sure about that. Yeah. No, in the product, there's no identity. There's no product and identity. There's no product. Yeah. It's the same. Essentially, the best way to think about it is really very much like minimal, like a most basic minimal model, which we now.
But minimal models contain the identity for sure in the OP. So
yeah. So there is OP. Yeah. Yeah, but it cannot be in the product of the
No, it is now.
Oh yeah, it can be. Yeah, okay. So in other words, in one of those OP, we should find it. I didn't think much about it.
Can I have a quick comment about this? If I understand correctly, this amplitude comes from the tree-level gluon amplitude,
yes.
Right?
Yes.
So there should be a more leading turn compared to this coming from the disconnected amplitude. I think that's what Miguel was trying to say.
Oh, that's what you are talking from.
Yes, well, I'm wondering what exactly is the prescription here for getting the correlate, because the disconnected diagrams, they behave differently because the delta functions, they are different, right?
Yes, the delta function in lambda will be different.
Yes.
But has someone considered these terms, or are we supposed to ignore them, or what is the prescription?
Actually, I will say a little bit about the disconnected amplitudes tomorrow in the discussion session, but maybe someone else has also thought about that. Yeah. Yeah, so I would say this is already the sub-leading term compared to the disconnect.
Yeah, naively, this is what I would say, but I don't know what the rules of the game are here. So
yeah, I don't know either.
Well, you start from the rule of celestial amplitude, which is from that point of view, like as a connected, amplitude. So I don't know.
But the kinematics will be different, right? Even the kinematic dependence on cross ratios for the leading
we can talk about four-dimensional kinematics and two-dimensional. I mean, four-dimensional.
I meant the two-dimensional.
Yeah,
I meant the two-dimensional. The two-dimensional kinematics.
Okay.
If the unit operator is in the OP, would that be coming out of the two-point function, for example? Because I guess if two operators, the OP has a unit operator, that means that the two-point function is not zero, correct?
Yeah.
Okay, so we have a two-point function between a field and a shadow field. So the unit operator appears in these OPs between a shadow field and another normal field. So we have a field that we compute with the shadow transform, and we take the OP with the regular field, then we can find a two-point function that's not vanishing.
Mm-hmm.
Yeah, usually we think about it the other way. You start off with an ordinary two-point function, which is well-defined, and it just so happens that in that case, if you take the shadow transform of one of the operators, then you get a delta function, so it disappears. I think what you're telling me is that in this story, it's the reverse. You start off with something which is zero, or it's just a delta function, and then you have to do this shadow transform to get something.
That's right. Yes.
Okay.
Yes.
Maybe I should just stop the discussion there. I guess the next talk should start, if I understand right. Thank you for all the questions, and I guess
let me get out. Let me stop.
So if you stop sharing,
of course.
And Anna, can you?
Oh, we need to. 1 second.
Oh,
I need to make Anna. Yeah, just a second. Let me make Anna a co-host.
Yeah.
Just a second, please. What?
Oh, okay.
You're all set now, right?
Share, yes.
Okay, thank you very much.
Okay, let's see. Screen. Okay, so can everyone see, and can you see the slides moving as well?
Yes.
Okay, so
so then I'll give you a warning 5 minutes before the end. And with that, then, so we're pleased to have our next speaker, Anna Raclariu, and she's going to tell us about conformal blocks and light ray operators in celestial CFT. Please go ahead.
Okay, so thank you very much to the organizer for inviting me to be here. I'm very happy to tell you about some recent work with Alex Atanasov, Walker Melton, and Andy Strominger, as well as some recent ideas based on some ongoing work with Laurent Friedel. So this talk is going to provide a complementary perspective to what Tomasz has told us in the previous talk. So let me start off by giving some motivation for why one should study celestial holography. So probably this is redundant for the audience here, but I'm going to do it anyways. So celestial holography is believed to provide a dual description for scattering in asymptotically flat spacetimes. So in particular, the celestial sphere is believed to be a natural place in which observables of quantum gravity, for example, are to be defined. So in particular, the S matrix in quantum field theory and quantum gravity can be recast as a celestial amplitude, which transforms nicely under the Lorentz group. So the idea is to study essentially scattering in the basis of boost eigenstates, as opposed to the standard energy momentum eigenstates one uses in quantum field theory and gravity more generally. So for massless scattering, this map is very simple. So the way this works is that one takes an asymptotic state of a massless particle, which is naturally labeled by 3 variables. So 2 angles and an energy. So we already have the asymptotic state as piercing a point on the so-called celestial sphere. So all we have to do to get from the spaces of momentum eigenstates to a basis of boost eigenstates is to trade this energy variable for a scaling dimension delta. And the way this can be done is by taking this an integral transform, which for the case of massless particles just reduces to a simple logarithmic Fourier transform or Mellin transform. And since the theme of today's workshop, of today's session is the bootstrap, I'd say that one of the goals of celestial holography is to kind of understand all of the symmetries and constraints governing celestial theories to ultimately sort of bootstrap scattering amplitudes in quantum gravity. So here there's been a lot of work recently and from different angles, different perspectives, using different approaches in kind of tackling this problem, so understanding what the celestial conformal theory, conformal field theory looks like. So originally I was going to put a list of references as well on the slide, but then I quickly realized that I would just fill up the slide with a lot of names. There's a lot of people, many of which are here today, who have been involved in this program. And there's been a lot of progress. But let me highlight some of the kind of topics which are going to be relevant for today's talk. So one of them is this idea that celestial amplitudes obey conformal symmetry. So why is that? That is just because the Lorentz group in 4 dimensions acts as the global conformal group on the celestial sphere. And so celestial amplitudes are constructed such that they transform as in the same way as correlation functions of primary operators in a conformal field theory. Then it's also known that in addition to being conformally symmetric, celestial amplitudes obey a bunch of other symmetries, perhaps the simplest ones being the ones coming from bulk momentum conservation. So those are known to sort of relate celestial amplitudes involving operators of different dimensions. Then there is a huge class of other symmetries which have to do with soft symmetries, which again involve insertions of operators of negative dimensions, and again provide a full set, like an interesting kind of very large set of relationship among, again, correlation functions of operators, involving operators with shifted dimensions. So today I'm going to focus on the most basic kind of symmetry, which is global conformal symmetry. And I'm just going to provide, in a very simple example, a conformal block decomposition for a celestial 4-point function. The outline for today's talk is as follows. So first of all, I'm going to review, or I'm going to present, as I said, the conformal block decomposition for a scalar 4-point function at 3 level in celestial conformal field theory. And the main results are going to be the fact that we're going to find in this decomposition is 2 sets of exchanges. So one of them is a set of massive scalar exchanges of positive integral dimensions, which can be interpreted as coming from sort of translation invariance in the bulk. And then the other set is a collection of spinning massive exchanges. So this is going to be a continuum, as we'll see, and it involves light ray transforms of massive scalars on the principal series. So put together, these 2 contributions can be then shown to actually generate the celestial 4-point function, where the operators, the external operators, are in the usual conformal primary basis. So not before taking any shadows, like Tomasz has discussed. So from this point of view, it's sort of complementary to Tomasz's approach. So, and then since these light ray transforms, these light ray operators kind of show up in these conformal block decompositions, it's natural to kind of think about what their role would be. And again, we're gonna, I'm sure we're gonna hear more about this in future talks, for example, by Atul. But I'm also gonna make some sort of comments on light transforms and shadows in celestial field theory. And then I'm gonna just end up by pointing out some open problems. Okay, so to start off with, the problem we're considering is a simple case of massless scalar 4-point scattering. And in this case, we know that in momentum space, a general scattering amplitude takes the form of a function of 2 Lorentz invariants, the center of mass energy S, and the momentum transfer T, defined in this way, multiplied by this momentum conserving delta function. Now, to get from this momentum space scattering amplitude to the celestial sphere, it turns out that for the 4-point case, all one has to do is to essentially consider just one Mellin transform with respect to the center of mass energy of the scattering amplitude. So first of all, let me just say that naturally, even in momentum space, such 4-point functions are already labeled by a cross ratio on the celestial sphere. So this cross ratio essentially arises by looking at the ratio of the momentum transfer to the center of mass energy upon parametrizing the momenta in a convenient way. So we already have dependence of the scattering amplitude on this cross ratio. And then the other variable, the celestial 4-point function is going to depend on, turns out to be this beta parameter, which turns out to be related to the sum of the scaling dimensions of the operators involved in the scattering process. So in some sense, we are trading sort of the bulk scattering angle for cross ratio in the celestial sphere, and we are trading the center of mass energy for this variable beta, which is the sum of these external dimensions here. Now, the other ingredients involved in the scattering amplitude, in the celestial amplitude, are this conformally covariant cross ratios. By construction, this has to be there. It ensures that these objects transform, like, as I said, correlation functions of primary operators under conformal symmetry. Then there is some other function which just depends on the cross ratio, and crucially also involves this delta function in z minus z bar, which comes from bulk momentum conservation. And then there is this piece, which is just, as I said, the Mellin transform with respect to the center of mass energy of the scattering amplitude. So just to briefly remind you, the reason why, so a priori, there will be 4 integrals. So 4 Mellin integrals, one has to perform with respect to all of the 4 external legs. The reason why we only have like 1 Mellin transform at the end of the day is because this momentum conserving delta function actually ensures that 3 of the momentum conservation constraints actually get saturated by 3 of the integrals. The remaining one turns into this constraint on the cross ratio, and then the final Mellin integral just turns into sort of this integral with respect to the center of mass energy. So this formula is a generic formula for scalar scattering. The scattering amplitude doesn't have to be 3-level. It can include loop corrections and whatnot. And again, I'm sure we're going to hear more about this in later talks. But today, I'm just going to focus on the simple case of 3-level scattering. And so if one looks at the scattering process in asymptotically flat space, so of course at 3-level for identical scalars, one expects, the 3-level amplitude has 3 contributions, an S channel, a T channel, and a U channel one. But again, for simplicity, it turns out that sort of the simplest celestial amplitude is associated with this T-channel exchange, which I'm going to focus on from now on. So I'm just zooming in into a problem which becomes tractable and solvable, as we'll see in a moment. So let's take this momentum space scattering amplitude. So using the map before, one can then just write down the associated celestial amplitude. So what one has to do is to perform this integral over a pole in S. And this can be done using complex contour integration. And one arrives at a formula which looks like this. So here, let me just point out that I've just rewritten the conformally covariant prefactor in a way which is more convenient for performing conformal block decomposition, as we'll see in a moment. So I'm replacing the conformal covariant prefactor, which is symmetric under exchanges of any 2 points, by 1, which is just symmetric under pairwise exchanges of 1 and 3 and 2 and 4 respectively, in which case the remaining functional dependence on the cross ratio Z looks like this. And so the goal now is to just perform a conformal block decomposition of this function f of t. So, and just to let you know where we're going, so the approach we're going to take is to first of all treat z and z bar as real independent variables, which means that we are working in a setting where our celestial conformal field theory is Lorentzian. And then we will be expanding this function of the cross ratio on a complete set of solutions to the conformal Casimir equation on 2 points. Over the Lorentzian square, where z and z bar lie between 0 and 1. So this has already been hinted upon in the discussion before and by Tomasz. So the reason we're restricting to z and z bar to lie between 0 and 1 is that these are actually the values they take in the physical regime. So essentially, for S positive and T negative, it turns out that z and z bar, the z and respectively z bar are constrained to lie in this interval. So in other words, the amplitude, the celestial amplitude we're looking at is only defined, is only non-zero inside this interval. Okay, so
sorry, can I ask a question?
Yes.
So, I don't understand, why is this well defined? Because you have this delta function, so I can multiply this f of t by lots of things that collapse to 1 with the delta function. This will give you a different conformal block decomposition. So why is this the canonical way of writing this f of t?
So this is not, well, the delta function, as we said before, the delta function in z minus z bar is there in all celestial amplitudes where you're not working in a shadow basis or a light ray basis. So this delta function of z minus z bar is going to be there. And then there's this other piece is determined, is completely fixed by this particular amplitude we're looking at. So of course, if you're looking like at an S channel amplitude, this functional this f of t is going to be different indeed. And in fact, for any scattering amplitude that you could be considering, this function is going to be different. We're just focusing on one particular example.
No, but what I'm saying is that why is ft canonically well defined the way that you wrote it? Because I can just multiply this by any function of z minus z bar, right? That collapses to 1 when z is equal to z bar.
Oh, I see what you're
It will
saying.
be the same function, but if you expand that function as conformal blocks, treating z and z bar independently, you're going to get a completely different result.
No, but I'm not stripping off the delta function in z minus z bar here. Sorry, if the delta function is there, I think that the answer, I mean, yes, you can multiply.
Okay.
You can multiply by a function which collapses. Yeah, for sure. So I should say yes, because that was the original goal, and perhaps, okay, I'm going to say later that perhaps the way to go is actually working in a different basis where this delta function gets smoothed out. But originally, and this is what we ended up doing in the end, was to kind of understand how this delta function arises from the conformal block decomposition, and this is one of the main results of this talk. So we're including it, and then this function is sort of, it's unique, I would say. So uniquely associated to this T-channel amplitude. Okay, any other questions? For some reason, I cannot see. I have two screens, but somehow I just thought I cannot see anyone. So please do let me know if there's any questions.
There's no hands anyway.
Okay, that's great. So I apologize in advance if I don't see. So somehow I don't have access to that little bit. Okay, so so what are we going to do? So the goal, as I said, is to perform a conformal block decomposition. And to do that, it turns out to be convenient to use some, so of course, these tools have been developed over the past years in the studies of conformal field theories. And the machinery involves these so-called conformal partial waves. And in particular, we're going to be using some formalism developed by these people here recently, where they constructed conformal partial waves in both 1 and 2 dimensions for Lorentzian conformal field theories. So the idea is to start with the conformal Casimir equation for 1 and 3, which takes this form. So this dz and dz bar are these kind of second order differential operators. So this equation is just a hypergeometric equation, and it has two well-known solutions in 2 dimensions. They are just these SL2C conformal blocks, which are just these hypergeometric functions. But the question here is, how do we construct actually a set of solutions to this equation which obey orthogonality and completeness relations? So the standard conformal block don't have these nice properties. However, these linear combinations of a conformal block and its shadow, so the shadow for SL2R takes a conformal block of dimension of weight h to a conformal block of weight 1 minus h. And so it was argued and shown in this paper that if one considers, so one can construct a basis for the SL2C conformal Casimir equation from solutions of the SL2R conformal Casimir equations in this way, by taking a product of 2 SL2R wave functions, which are linear combinations of the SL2R block and its shadow. And here it's important that the basis is formed by, so this basis is labeled by these dimensions of the exchanges, which lie on the so-called principal series. So they have dimensions h a half plus I lambda, where lambda is a real number. Okay, so so this can be shown, and the question is, okay, what are these coefficients Q of H, which ensure that these solutions are orthogonal and complete? And for certain choices, I haven't written them down here, but they've been found and they're well known, and we have used them. One can show that the inner product of such 2 SL2R conformal partial waves is proportional to the sum over delta functions. In other words, these conformal partial waves are orthogonal. And similarly, by integrating over H's over this principal series, one finds that, that these wave functions are also complete. And so then by extrapolation, so this can be shown for the SL2R conformal partial waves, and because the SL2C conformal partial waves over in Lorentzian signature can be shown to be products of these, can be chosen to be products of these SL2R wave functions, it follows that the SL2C ones are also orthogonal and complete. So we'll be using these to just perform a conformal block decomposition of this function ft of z and z bar. So first of all, so here is the function again we're interested in, and the first step is to just write it as a linear combination of these conformal partial waves with some coefficients, which here we're calling g of h and h bar. And these can be found essentially by taking an inner product of the left-hand side, so of our celestial amplitude, with these SL2C or SL2R cross SL2R conformal partial waves. So orthogonality ensures that on the right-hand side, when I take this inner product, I'm just going to isolate these coefficients, g of h and h bar, while on the left-hand side, we will we'll get the results. So essentially a formula for this for these g functions. And then upon plugging back in these functions we obtained via this procedure, one can deform these contours and pick up the poles, the combination of poles and coefficients and partial waves to deduce the conformal block decomposition. So it turns out that for this simple case of the amplitude, our analysis is very much simplified because these functions g actually turn out to be proportional to delta functions in h and h bar. So one of the integrals, sort of integrals here can be easily performed, and then at the end of the day, one just has to deform one contour. And upon doing that and picking up the poles, one finds sort of a formula for this delta function in z minus z bar multiplied by this function of z. And the formula looks like this. So it has essentially two contributions. So the first contribution, one can see that it involves exchanges of dimension delta equal to 1 plus n and spin equal to 0. So we have this discrete tower of positive integer dimensions. And moreover, one can match, so up to these cosine functions, which are still quite mysterious, one can match the coefficients of these conformal blocks with products of coefficients of 3-point functions of 2 massless scalars and 1 massive scalar. So the idea is that this coefficient essentially precisely matches this 3-point function involving 1 massive particle, which leads us to kind of deduce that the exchanges coming from this first set of from this sort of first contribution to this function are associated with just massive exchanges, massive scalar exchanges of integer positive dimensions. Okay, so and this I should say that this may be expected by translation invariance, because we know that translations on the celestial sphere actually shift the dimensions up by 1. Then there is a second contribution, which at first we are more puzzled by, which involves these exchanges of dimension delta equal to 1 and imaginary spin. So these are these sort of complex spin operators, which Tomasz nicely was able to get rid of. But you know, if you just consider the original correlator without having any prescription of like shadow transforming or making them single valued or whatnot, they just show up. And again, they're here, and they can be associated again with light transforms of massive scalars. on the principal series this time. So in particular, these coefficients here exactly match these associated 3-point functions involving 2 massless scalars and 1 massive Lie transform of a scalar particle on the principal series. And similarly, I should have also said that this D is the inverse 2-point function coefficient of 2 massless, 2 massive scalars or their Lie transforms respectively. So things come into place pretty nicely. So this is how this celestial amplitude looks like when one decomposes it into conformal blocks. I should also say, because there was some comment or some question in the discussion beforehand, so one can also explicitly check that if you deform the contour here, one can also do that, but one can only deform the contour when Z is different from Z bar. And in that case, one can show that precisely the result obtained upon doing that contour deformation exactly cancels this first piece, which is expected because we know that this correlation, this celestial amplitude actually vanishes for Z different than Z bar. So this is a check that this formula is correct. And then moreover, one can also show that this delta function in Z minus Z bar actually arises from this continuum integral here. So one can study sort of this integral in the limit when Z and Z bar are small, and then can show that this is how this delta function of Z and Z bar arises. So it comes from this continuum block. So these are 2 take-home messages. So now let me
just give 5 minutes.
5 minutes, perfect, yes. Mm-hmm. So let me just make a couple of comments. We see these light ray transforms showing up. So one thing one can do is to identify them actually with conformal primary solutions to the wave equation. So in particular, if one has starts from a usual conformal primary wave function of a scalar particle, which takes this form and does a left moving, for example, light transform on it, one obtains sort of a conformal primary wave function of dimension delta equal to 1 and imaginary spin. So this is just to say that these light ray solutions have a bulk interpretation as conformal primary solutions to this kind of scale to the wave equation. And then, and so this again, I'm sure we're gonna hear more about in later talks, but there's been this proposal which was put forward that 2- and 3-point functions involving massless particles, which typically have these annoying delta function singularities, which again come from momentum conservation, can actually be smoothened by considering shadow transforms or light transforms. So again, we've seen an example of this already in Tomasz's talk. But even if one considers a 3-point function, so even a simpler kind of situation, there is a prescription which is given by Sharma that one should consider right-moving light transforms of these negative helicity operators and left-moving transforms of the positive helicity operators. And what this prescription would ensure is that all 3-point functions, which are naively singular, actually get turned into the more familiar usual CFT 3-point functions. So this raises a natural question about what the prescription would be to actually, what the basis would be in which one should compute celestial amplitudes. And so I should say that shadows, again, they also could provide a way forward, but again, for 3-point functions, it's a bit less clear what the prescription would be in finding such a basis. But in any case, so regardless, we have quite a lot of evidence so far, both from Tomasz and other work, that either shadow transforms or light transforms or both will play an important role in kind of defining a good basis for celestial conformal field theory. So it's then kind of natural to ask the question, well, if this is going to be a good basis, even if we don't know exactly what the prescription would be, it would still be interesting to study how, for example, symmetry generators look like in this new basis. And this is in fact one of the questions we asked with Laurent Namely, we tried to kind of understand how, for example, momentum generators look like in a shadow basis or a light basis. And it turns out that there is a nice compact formalism which allows you to take these to kind of conjugate momenta by shadows and light transforms and kind of obtain very simple formulas for all of these generators. And here is one example of how a shadow of a massless momentum looks like. So it involves these derivatives, so it might look a bit funny, but it's also kind of familiar if you remember the expressions for massive momenta, which were written down by Lorenz-Lanikov before. So they kind of look like one piece, almost look like they have pieces which resemble those entering the definitions of massive momenta. And then and there are similar expressions for light transforms, and similarly they involve such derivatives. And the point is that what one can do with these is to actually use them to derive constraints on celestial amplitudes involving shadows and light transforms. So this is something we're currently thinking about. So so this brings me to the end of my talk. So I guess I'm running out of time, but here are some open questions, where one of the first ones would be to kind of find a principle which dictates the choice of a good basis for celestial conformal field theories. And then, there are two approaches. Either one could guess what such a basis would be, and then try, do some trial and error calculations and kind of try to see how amplitudes transform to this basis and figure out how sort of symmetries act in both Poincaré and soft symmetries and so on and so forth. And to some extent, in this work with Laurent, we're kind of trying something out like that. But of course, having a fundamental principle which dictates this good choice of basis, that would be great. But I would say that it's still an open question. And then once one has found such a good basis, the natural step to do would be to kind of consider 4-point functions and conformal block decompositions in this new basis. And to some extent, we've already seen some example of this approach in this very interesting work here. And of course, at the end of the day, one may hope that some simplifications would occur in this nice basis. And finally, it would be very interesting to study the constraints, these associated celestial amplitudes or the bay. And ultimately, I would say that that one of the goals would be to kind of use all of these ideas to infer something about quantum gravity in asymptotically flat spacetimes, and in particular, non-perturbative properties of scattering amplitudes in this context. So thank you very much, and I'm happy to answer any questions.
Yes, thank you for that lovely talk. To thank Anna. And of course, if there's any questions, please just raise your hand in the chat or in the raise your hand. Okay, I think. So actually, let me ask. So you have a particular, you choose a particularly simple amplitude, this T-channel amplitude.
Yes.
Is there any thought that, in some sense, if you had that the basis could be suited to different theories? So for example, if you had, a Yang-Mills theory where there's sort of other symmetries and so on, that a different basis would be more appropriate.
Yeah, that's possible. And in fact, in Tomasz's talk, we kind of saw something like that. But of course, I would say that at the end of the day, it would be nice to have like an approach which kind of unifies the treatment of all of the theories, like rather than just pick a basis for like one theory, another basis for another theory. I'm not sure if this was your question. At first, I thought you were going to ask.
It is. Oh, go on, yes.
At first, I thought you were going to ask, okay, we considered a very simple example, and it turns out that there are these nice simplifications in this particular case, but what about like any other kind of amplitude?
Right.
And the answer to that is actually that we have considered. So I just talked about the T-channel one because it was simpler, but one can also do, for example, S-channel and U-channel decompositions. So there are simple formulas on the celestial sphere However, the compositions here, they look much more complicated. And in particular, these coefficients here in, for example, the S channel, for the S channel case, as well as the U channel case, they don't obviously, for example, factorize. So they involve, the coefficients themselves involve generalized hypergeometric functions. And I'd say that understanding how those arise from 3-point amplitudes, and even as perhaps there is some kind of degeneracy at all these levels coming from some symmetry or something, but like understanding it, I think it would be remarkable to sort of understand how those more complicated decompositions arise from building blocks like 3-point functions. So this is just to say that one can do, and in fact, there is some interesting work by Volovich and collaborators where they similarly computed some other 4-point functions in other channels, and it's interesting to understand that.
Tomasz, you had a question? I think you might be muted.
Yes, thank you. So I think a nice thing that you have, at least in one channel, you have agreement with OP, if I understand, yes? So
yes.
You got but now the beta function, I think you're understanding T channel. So you are talking about T channel. So this OP is in the T channel. It involves one incoming and one outgoing particle, yes? That's what you say?
By T channel,
I'm asking that because then OP is different for two incoming or one outgoing and one incoming. So which beta function you get here?
So for when you have two massless and one massive particles, this is the, well, one can, of course, first of all, it's an incoming massless and outgoing massless and a massive particle. So in that case, first of all, one has to work in Lorentzian signature because otherwise the 3-point function doesn't even exist. But I think for that case, so I think you're wondering, the OPE case we considered with Monica involved. I think in both cases, this is the answer, that it's the beta function. It's a beta function of this form, right? Because it's not exactly, it singles out a dimension. It looks like delta 3 plus delta 1 minus delta 2, and delta 3 minus delta 1 plus delta 2, where delta 3 is the dimension of the massive particle. And these ones, 1 and 2 are, of course, they have to be symmetric. But it's scalars. And I should also say that this is the scalar case. So I don't think there is this one, I don't think there's different. No, one can compute it. And this is the answer for two scalars going, two massless scalars in a massive scalar. So it's a bit different from the gluon case, if this is what you're asking. But of course, they ought to be related at the end of the day. So in particular, it would be interesting to understand how this beta function is related to the one we see in the gluon case, the ones we see in the gluon case. Does this answer your question?
Yes. Thanks.
Okay, there's more questions, or?
I think the chairman somehow has disappeared, but maybe Andy's next question.
Oh, okay. Yeah, you've talked about looking for a good basis among, by light transforming or shadow transforming or so on. But I wonder if you could also comment on the issue of what the right choice of, surely we can't be taking all conformal weights. So there's unitary principal series and there's integers, and how are you thinking about, could you comment?
Yeah, that's an interesting question, but I guess we know we all discussed it, but I don't yet have an answer to that question. So here in this work with Laurent, we're being agnostic to this weight so far. So because whether you restrict to the weights or not, like at the end of the day, you're still gonna, like these formulas are gonna apply for whatever the weights are gonna be. So then at the end of the day, yes, of course, we're gonna have to restrict to some set of convenient weights. And of course, as you know, it would be nice if the basis we found involved integer, but like negative integer, positive integer dimensions instead of these dimensions on the principal series, because those would naturally, for example, allow for translated operators. Those should be, yeah, somehow part of.
But we have no reason to expect, do we, that that we should get a good conformal block decomposition that obeys all the good properties, unless we both have, unless the basis is completely right, including the restriction to the weights, right?
Yeah, I agree. So here, for example, yeah, somehow I think here we get a mix of things. Yeah, it's a bit confusing. I agree. Yeah, you would want, of course, you'd want the operators which appear in the exchanges to be the ones you're allowing for in your basis as well. So they should be there. Oh, but here, right, these are just related by a light transform. So that's sort of like a change of basis. So I don't know, maybe it's sufficient to just consider, for example, positive dimension operators and, or yeah, I don't know. But yeah, it's a good question. Yeah, I don't know what the prescription is.
I guess if we have a good basis, we should expect the OPE closes.
Mm-hmm.
We should expect that that only those states appear in the conformal block expansion.
Yeah.
Yeah, those are, I think, probably necessary, but maybe not sufficient.
Yeah, no, I agree.
Oh, and they should be, yeah, they should be local. I guess that's the same as mutually local. I guess that's the same as a good OPE.
Mm-hmm. Yeah.
I guess if there's no more questions, I'll hand back over to the organizers to announce the break.
Okay, so there will be a break and we will resume at 5:20 European time for Sabrina's talk. Which is -6 hours East Coast.